So, in our previous segment, we established that engineering, in general, is about applying math and science for the development of a wide range of products and processes that can serve a practical purpose. And we also noted how this development that we speak of there is what we refer to as the engineering design process. In this segment, we are now going to broadly overview what that process tends to involve and introduce some of the typical stages and tasks that tend to be associated with it. Now, it's important to appreciate here that although the design process has certain typical elements, it is also very flexible and open-ended. It is not rigid or formulaic. This is a theme I'll be coming back to a lot in the coming lessons. But for now, just try to keep in mind that there is a balance to be found between understanding the core elements and also learning how to adapt those elements and the overall process to suit each particular situation. And those situations might vary by the particular discipline of engineering that you're working in. It could vary by the company or organization you're working for. It could vary by the particular product or process being designed, and various other factors as well. So last time we talked about the definition of engineering. I mentioned how there are various definitions out there, and we looked at one notable one put out by ABAT. Let's now do the same for the definition of engineering design. Here's ABAT's definition. Engineering design is the process of devising a system, component, or process to meet desired needs. It is a decision-making process, often iterative, in which the basic sciences and mathematics and engineering sciences are applied to convert resources optimally to meet a stated objective. It is essential to include a variety of realistic constraints such as economic factors, safety, reliability, aesthetics, ethics, and social impact. Now, the first thing I notice about this definition here is how much it seems like a rephrasing and elaboration of the definition of engineering that we talked about last time. And this makes sense because, after all, the engineering design process is really the heart of engineering. So notably, we have there the goal of meeting an overall objective through the application of math and basic science and engineering science. By the way, engineering sciences are fields that can serve as sort of a helpful bridge between the so-called pure sciences that we discussed last time and engineering itself. They're fields that are cultivated beyond purely observations and analyses of natural phenomena, but they are broad enough to be themselves applicable to solving a wide range of problems. So, for example, circuits and certain aspects of mechanics would fit in that category. I also just want to say something about this definition's reference to systems, components, and processes. Now, I've been using the phrase products and processes, so I've been referring to products to essentially cover systems and components collectively. Now, systems can arguably be broad enough to encompass just about any conceivable type of product, even relatively simple ones. But a component specifically refers to products that are intended to be used in other products. So I just want to say something about this. A component can be something that you're designing for the broader system that you're also designing. It could be whether that's part of the same project or a different parallel or subsequent design project. But it could also be that a component is being designed for a wide range of potential uses in other types of products. So For example, a new mechanical part could be developed that in turn has potential applicability in a wide range of machines, for example. Or a new software module could be developed that has the potential to be incorporated in a wide range of other programs. Now, the next thing I notice about this definition is how it frames the engineering design process at its core as a decision-making process. So this really makes sense. This is a useful way to think of engineering design as a decision-making process. Because regardless of what stage you're at or what task you're doing, there is always decision-making involved, and it's really at the core of what we're doing. And notably, another key decision that has to be made, often many times through a given process, is about the iteration, which brings me to the next point that stands out in this definition, which is that the process is often iterative. I would say nearly always iterative. By iterative, we simply mean that certain parts of the process in any given situation are going to need to be repeated. Which parts need to be repeated and how often for each, or whether the whole process needs to be repeated and how often, that is all very, very different based on each situation. This relates to what I talked about a moment ago when I said that the process is not rigid or formulaic and it needs to be adapted for each situation. Those situations can vary based on a lot of factors, but the judgment, and we talked last time about the role of judgment. Well, one of those judgment calls that's very critical is deciding which aspects of the process to reiterate, in what way, how much, and when you're done, or at least done enough for the purposes of a given design process. So this ties in the role of judgment, and it also brings in this critical idea of the role of failure. It's really important to understand early on in your learning about engineering design that failure cannot be feared. Failure is a critical part of how we learn the best way to adapt and apply these general principles of engineering design to each unique situation. While we obviously want to do whatever we can to maximize our chances of succeeding as soon as possible, we also have to really appreciate the value of failure and its ability to teach us how to move forward more effectively the next time. Sometimes that next time is not even your next project, but the very same project in the next iteration. Another point I want to make here, somewhat related to that point on failure, is that a key part of what distinguishes engineers from other inventors and makers of things is this methodical design process that we follow. So what this means when it comes to interpreting our failures is that we can't judge the value or correctness of a decision solely by its outcome. It's possible to invent something great by just winging it, not going through a methodical process, not doing all the things that we're going to talk about with all the steps and stages and carefully managing the iterations and thinking through the right way to proceed at each step. It's certainly possible to do that, and it's wonderful when it happens, and that's great. But it's what distinguishes engineering as a profession and as a discipline is that we do have, in addition to our formal training in math and science, which is one key aspect of it that we already covered, But another key distinction is that we do have a methodical process. Now, yes, it's not rigid, it's not formulaic, it's flexible, but it's not a free-for-all either. It is structured enough and methodical enough that it meaningfully distinguishes engineering from other modes of inventing and creating and tinkering that people might engage in. So when I teach design, particularly at the introductory level, one of the things that tends to surprise my students the most is when I tell them that their project will not be graded based on how successful it is. It will not be graded based on how well their product or process actually meets its stated requirements. And this is kind of mind-blowing for many of them when I first explain this, but the first priority in getting acquainted with the design process is going through that process. It's learning how to give each step, each set of tasks, its proper attention, meaningful consideration, make careful judgment calls, and if you end up getting through one cycle and you don't meet all or even most, or hey, maybe even not any of your requirements, that is not necessarily a problem, because it could very well be that that team still carefully, methodically applied all the various tasks and steps of the process that I asked them to address. And this is particularly true at the introductory level, where learning the fundamentals of the process is really what's most important. It is true, of course, that at more advanced levels and certainly on the job, part of the judgment and skill needed for engineers is to negotiate an overall scope that gives them a reasonable chance of fulfilling most, if not all, of the requirements within the allotted time and budget and so forth. But at the introductory level, the main focus is just on getting acquainted with those steps and elements and tasks of the process, so that those foundational experiences can begin to take hold, which is the basis for cultivating the very judgment that will increase the chances of success in subsequent experiences. Okay, so the next thing I want to talk about here is this notion of how there is often said to be different levels of originality to engineering design, depending on how new and different the ideas being developed are. Various authors have come up with various ways of breaking this down and articulating this range. I'm going to briefly introduce just one example approach here, just to give you a general sense of what I'm referring to. But keep in mind, this is just one of several ways that different people have proposed thinking about this. Okay, so in this approach by Paul and Beitz, we have essentially three categories. Original design refers to when the overall solution principle is fundamentally new. Adaptive design refers to when we're using an existing overall solution principle, but embodiments are adapted according to the particular design requirements. And variant design in this paradigm would refer to situations where we're simply selecting from predetermined options or working within predetermined ranges that an existing design establishes for us. Now, I want to make a few points about this breakdown. And the first one is how much gray area it has. So there are no clear, bright lines here. It's very subjective, particularly the line between original and adaptive. So, for example, while there may be fairly broad agreement that the automobile counts as an original design. Many of the advances in automobile technology since then could be debated as to which side of that line they fall on. So an awful lot of things could be considered adaptive design. And I really think it's more helpful to think of this as more of a spectrum or range as opposed to discrete categories. Now, the second general point about this that I want to make is that no particular level of originality is inherently superior. So while highly original designs can be very intriguing and quite groundbreaking when successful, they also might not always be necessary and can entail a level of risk that may or may not be appropriate for a particular situation. And notably, it's sometimes adaptations of pre-existing concepts that make the critical difference between an interesting idea with a lot of potential and something that can actually be put to a practical use to create a significant benefit. Many of the most successful technological innovations were clearly adaptations of pre-existing concepts. The story of the light bulb is actually a classic example of that. Also, keep in mind that even less seemingly profound sorts of adaptations can still be very important. Incremental refinements or changes to suit a different context of use might not seem as exciting, but they are vital to the long-term success of many different technologies. The third general point about this that I want to make is to emphasize that originality is not the same as complexity. In fact, highly original designs can be quite simple and elegant and not complicated at all. Okay, now, the last thing I want to cover in this segment is the actual stages or steps of the design process. Before I get to that, I need to say something very important, and I can't stress this enough. There are many, many, many different ways that the engineering design process has been articulated, subdivided, and graphically depicted. And it is a good idea to do a simple internet search and get a sense of the vast range of descriptions out there for the process, both because you'll get an appreciation for how they differ, and also because you'll get an appreciation for how they tend to have core conceptual overlap for the key aspects, despite the differences in wording and organization and other things. Also, keep in mind that while various descriptions of the process can be useful, they're always going to have pros and cons. So, for example, more detailed descriptions can provide a lot more guidance for situations where they're applicable, but by that same token, that additional detail means that they're less likely to be as applicable in as wide of a range of situations. Conversely, more simple and abstract descriptions of the process are likely to be true for a much wider range of contexts, but they're not as informative. Having said that, for purposes of this lesson, I'm going to lean towards using a more abstract breakdown. Later on, I'm also going to talk a bit more concretely about the process of fleshing out and customizing these stages and steps for particular situations. Okay, I've put this off long enough. This is the basic breakdown we'll use here. We can think about it in 4 broad categories, each of which could be thought of as a stage or multiple stages. They are problem definition and design requirements, ideation and evaluation of design concepts, detailed design and prototyping, and verification and validation. Subsequent lessons will get into these each in more detail, but for now let's just briefly introduce each of these a bit more. So, problem definition and design requirements. This is where we broadly frame the problem that we're looking to solve and then flesh out or establish particular requirements by which we'll judge whether we were successful or how successful we were. For ideation and evaluation of design concepts, this is where we generate different conceptual ideas for how to solve our problem and decide which one or ones of those candidate concepts should be developed further. Detailed design and prototyping refer to that further development that I mentioned, and verification and validation refer to how we evaluate what we developed. Now, a couple important points about what I just told you. First, despite the default sequence that this seems to have, it is emphatically not a linear process. I can't stress that enough. It is not linear. There are a couple of senses in which it's not linear. First, remember what we said about iteration. Note how this process, even at a fairly generic level, is highly iterative. You might go through the whole loop several times. You might have partial subloops. You might repeat the same step or some subpart of a particular step. You might jump around depending on the situation. So the nature of iteration, as we discussed before, makes it profoundly nonlinear. Another sense in which it can't be considered linear is how flexible we need to be throughout the process, because we have relatively little visibility for what the later stages of the process are even going to look like when we're in the earlier stages. Oftentimes even within an initial iteration, because even if you have a general idea of where you're going, a lot of the specifics are going to depend on what happens in some of those earlier steps. Another general point to note about the stages as I broke them down here is that for products, for physical products that are going to be manufactured, as in mass produced, there are typically going to be some additional steps that I'm not getting into here. We'll say a bit more about why that's the case in another lesson, but for now, just keep that in the back of your mind. And of course, some engineering disciplines are more likely than others to have that be a concern. I just want to close out this segment with a brief comment about how frustratingly inconsistent the use of terms can be in engineering. Terms like specification and prototype, for example, carry a wide range of different meanings based on particular contexts. So just beware that in general usage out there, you can't necessarily assume you know what somebody is referring to just by use of those terms. You need to know the full context, which can be a little frustrating at times, especially for somebody who's just getting familiar with all these terms and concepts. But it's the reality. Sometimes these differences vary by engineering discipline, which can be important to note when collaborating with people from other engineering specializations. Sometimes it depends on the company or organization, which can be important for any sort of collaboration or interaction with folks from a different organization or who are used to something different. Sometimes it depends on the particular product or type of product being worked on, and sometimes it's a matter of personal preference or habit. So whatever the case may be, just be aware that inconsistent usage of a lot of this language is a reality we have to be mindful of. In the subsequent videos, we'll look more closely at each of the respective general stages that I introduced here, starting with what is usually the first, or among the first, defining the problem. See you then.